Welcome back to another lecture of derivation of beams. Here is a balanced steel ratio. First of all, what is steel ratio? Steel ratio is the area of steel divided by BD, means B is the width of the beam, D effective depth of the beam. Rho is the reinforcement ratio or the steel ratio. What is balanced steel ratio? It is corresponding to that amount of steel which will cause yielding of steel at the same time when concrete crushes. Means yielding of steel and failure of concrete occur simultaneously. At ultimate stage, here when the strain when the concrete strain is 0.003, at the same time the strain in steel will be equal to yield strain. Okay, here the strain in steel will be yield strain and stress in steel will be yield stress. Okay, here is a concrete ultimate strain. From the internal force diagram, CC, okay, due to stress 0.85 fc prime b into ab. Okay, we are talking about the balanced steel ratio. So the ratio will be balanced, area of steel will be balanced, whatever the area of steel that will cause the balanced steel failure. Okay, so all the things will be balanced. So that's why AB is the Whitney stress block diagram. Depth will be also A balance. AB, depth of equivalent rectangular stress block when balanced steel ratio is used. Okay. Balanced steel ratio. Okay, here is a tensile force AS into Fy. Here area of steel will be rho balanced into BD. I have already explained that will be rho B and that will be AB. Here area of steel will be rho balanced into BD. Okay, that will be steel ratio into BD. Fy will be as it is. For longitudinal equilibrium, okay, T will be equal to Cc. Here T value as it is and Cc I have shown in the previous slide. So after equating you will get rho balance will be equal to 0.85 Fc prime AB over Fyd. So we when we design the beam, we have the property Fc prime, Fy, depth of the effective depth of the beam, but we do not have the A balance. So how to calculate AB? Here balanced steel ratio. Here is a strain diagram. Okay, same I have shown in the previous slide. At top strain 0.003 and at bottom strain that will be equal to yield strain. Okay, from similar triangles ABC and AED, ADE. Okay, here 0.003 divided by CB and here strain Y divided by D minus CB. D is the effective depth. When you minus CB, then you will get this depth, D minus CB. Okay. Here, after cross multiply, you will get this CB value equal to 0.003 D, 0.003 plus strain Y. So that's all for the CB. But for simplification, I am just move ahead. But this is the final value of CB. If you have the value of CB, then you can get the value of AB easily. Why? Because AB is equal to beta 1C. Now I have just put the value of strain Y, that is Fy over Es. D is come out D, then multiply with Es, my modulus of elasticity of steel, and divided by modulus of elasticity steel. Es basically 200 into 10 raised to power 3 megapascal. I will just multiply on top and bottom. Es will cancel. Here after cancellation, then just multiply, you will get the value of Cb. When you will have the value of Cb, then you can also calculate the value of AB. AB is beta 1 Cb. You will put the value of Cb, you will get the value of AB. Now you will put back the value in the formula of rho b. Okay, in the formula of rho b, you will get the value of rho balanced. Okay, now all the values are known. Okay, there are three types of sections that are designed based in the concrete structures with respect to flexure at ultimate load level. First, tension control sections. Second, transition sections. Third, compression control sections. Okay, I will discuss one by one. Tension control sections. These sections are defined and are designed given by the guidelines by this course is basically as per ACI. So these guidelines are given by ACI. A section in which the net tensile strain in the extreme tension steel is greater than or equal to 0.005 when the corresponding strain in concrete at the compression phase is 0.003. What it means? It means when the strain diagram, when the concrete strain is 0.03 and the stress in steel and strain in steel is equal or greater than 0.005, then the section will be called tension control section. If any section have the strain in steel greater than 0.005 and at this when the corresponding concrete at the compression phase is 0.003, then this section is called tension control section. Now by similar triangles, okay, 0.003 divided by C equal 0.005 divided by D minus C, as it is equal and greater 0.005 divided by D minus C. Now again cross multiply, you will get the value of C, okay, 1000. When you will remove the dot, you will divide by 1000. After dividing, you will get the value of C, and if you have the value of C, you can get the value of A. Okay, now the second section, transition section. The section in which net tensile strain in the extreme tension steel is greater than yield strain but less than 0.005 when corresponding concrete strain is 0.003, that is a transition section. Here, if strain in steel is greater than yield but less than 0.005, that is called transition section. Here if you have value of A is greater than uh, uh, in the tension here, if your value A is less than this, then you have a tension control section. If your value of A greater than tension control but less than A balance, then you will have a transition section. Okay, what it means, for example, in tension control, if your equivalent stress block depth is less than this value, then you will tension control section. If your A is greater than, then you will have transition section, but A should be less than again A balance, greater than this but less than A balance. Transition section. Some guidelines for the transition section to ensure under reinforced behavior. Under reinforced behavior, ACI code establish a minimum net tensile strain of 0.004 at the ultimate stage when the concrete strain is 0.003. Okay, for transition section, ACI also given the guideline of 0.004. Again, similar triangle, 0.003 divided by C, 0.004 divided by D minus C. Okay, cross multiply, you will get the value of C, 3 by 7D, and you can also get value of A, just as we know A is equal to beta 1C. Both tension control section and transition sections are under reinforced section. What does it mean? Under reinforced sections are ductile sections. All these sections, in all these sections, first steel of the concrete section fail, then the concrete crush. Okay, in tension control section and in the transition section, first steel yields, then concrete crush. That's why these sections are called under reinforced sections. In under reinforced section, steel start yielding before the crushing of the concrete, means rho value is less than rho balance. It is always desirable that the section is under reinforced, otherwise the failure will initiate by crushing of concrete. If your steel is so much strong, then steel will not yield and failure will be crushing by concrete. This will be sudden failure, and that is not desirable. We always desire our steel first yield, then concrete crush. As concrete is a brittle material, so this type of failure will be sudden, which is not desirable. Okay, we want ductile design. Now the third section is the compression control section. In the compression control section, the section in which net tensile strain in the extreme tension steel is less than yield. Means in this type of section, the strain in steel less than yield, mean steel will not yield when the corresponding concrete strain is 0.003. In third type of section, concrete crushes, steel will not yield. That is called over reinforced section. In this capacity of steel remain unutilized, mean we have provided the steel in the section but its full capacity is not being utilized. It gives brittle failure without forming. This is most undesirable section, compression control section. In this section, A is greater than A balance and C is greater than C balance. Now, strength reduction factors. For tension control, these are the factor of safeties on the material side. For tension control, phi value is 0.9. For compression control section, member with lateral ties or stirrups, that is phi will be 0.65. Members with spiral reinforcement, phi with 0.75. This spiral reinforcement mostly comes in our column sections, so that's why that will be used in the 0.75. For transition section, mean between tension and compression control sections, for transition section, phi is permitted to be linearly interpolated between 0.65 or 0.75 to 0.9 here. If our section is compression control, the phi value will be 0.65. If it is a tension control, that value will be 0.9. Similarly here, strains. If our strain value is greater than 0.005, then that will be tension control, less than yield, compression control, in between transition. For transition, here is interpolation. You will get the strain in extreme tension steel when the concrete crushes. You have to calculate the value of strain. Then you will get the by interpolation value of phi, or you can directly use the formulas for members with ties, for members with spirals, for transition section strength reduction factor. Now maximum steel ratio. For maximum steel ratio, we want steel yield. T is equal to C, AS is equal multiplied by Fy, mean yielding of steel, that is desirable, equal to 0.85 Fc prime into B into A. B, just AS put the value rho into BD, B will cancel out, then the remaining rho will be here. Okay, then for the tension control section, strain in steel, that is 0.005. At that time, A will be beta 1 3/8D. We will put that value and we will get the maximum steel ratio for the tension control section. Similarly, for transition control, we will just put the value of A and we will get the rho maximum for the transition section. Okay, now minimum reinforcement for flexural members for beams, okay, that is under root Fc prime divided by 4 Fy should be greater or equal to 1.4 over Fy. The minimum steel is always provided in structural members because when concrete is cracked, then all load comes on steel. So there should be minimum amount of steel to resist that load to avoid sudden failure. It means if in your calculations due to very low loading, no steel required, but you have to must provide the minimum steel. For example, if by chance there is heavy loading, if there is failure in the concrete member, then at that time minimum steel must be present to take that load to avoid sudden failure. This formula is not used for slab. This formula is for beams. So that's all. Have a nice day.